So I'm going to say just a very small amount about Diophantus and Diophantine equations. Basically, I'm just going to say give one example of kind of the problem that he posed and how he solved them, and some small relations to other things. Diophantine equations are a huge topic that don't really belong in this sort of class, except to just to say here's what they are, and then when you take other math classes, you can see those there. So for example, if you were to take one of our algebra classes, you would see Diophantine equations there in a very like abstract way. And then if you were to take, I think, like a number theory type class, you would see it there as well, like an elementary number theory class, and other places as well. Maybe some of these transition classes and things like that. Anyways, so Diophantus, he was a Greek mathematician. One of the things that he did do was he introduced like symbolic notation that's more similar to what we have, rather than just kind of only stating, reasoning in words or pebbles or whatever, kind of using notation. You can look in the book. I think his notation is still confusing, but a lot of that is probably just because I'm not used to it, rather than there being something inherently confusing about it. Anyways, so I'm going to give one example of the type of problems that he looked at and kind of his solution technique. So the first problem, or the only problem, is to separate a given square into two squares. So to separate a given square into two squares. Okay, so he uses, to illustrate his method, he uses the number 16. So we could have something like 16 equals a squared plus b squared. Okay, we want to find a and b. Now, importantly here, a and b are allowed to be rational. We're not just looking for integer solutions. A and b can be rational numbers. Okay, so here's how he does it. He says, well, we're just going to call the first solution z, and then so the second one obviously has to be 16 minus z squared. So the second one has to be 16 minus z squared. Or the square of the second has to be 16 minus z squared. And what he further assumes, just to get an equation that we can solve, he further assumes that the second solution is 4 less than an integer multiple of z. So he assumes that this is kz minus 4. Okay. Well, now what we can do is we can solve this, using modern language. We can solve this for z in terms of k. Okay, so we can go ahead and do that now. We can solve this for z in terms of k. I knew there was something wrong. It should be a squared, because 16 minus z squared is that. Okay, so now just foiling that right-hand side there, we're going to get k squared z squared minus 8kz plus 16. The 16s are going to cancel. The 16 there and the 16 there are going to cancel. And if we rearrange things, we get 8kz is equal to k squared plus 1 times z squared. Now canceling a z on both sides. So z equals 0 is going to be one solution. Obviously if z equals 0, b can just, b squared can just be 16. So z equals 0 is a solution, and then if we divide by that, we get 8k is equal to k squared plus 1 times z, and then so z is going to be equal to 8k over k squared plus 1. So that's what z is going to be equal to. And then, okay, how do we get, so what we're going to do now then is this is z, so the other square is going to be 16 minus this. Okay, or it's going to be 16 minus this squared. Okay, and so what this does is it gives us rational solutions to this equation right here. Okay. In particular, this is one solution, and then if we do 16 minus z squared, if we do 16 minus z squared, sorry. Wow, where did my notes go here? Okay. 16 minus z squared is equal to 16 minus 64k squared over k squared plus 1 squared. And now this simplifies to the following. Obviously, I could just do the algebra on the board, but that takes too long. So it's going to be 4k squared minus 1 over k squared plus 1, and all of this squared. Okay, so this is 16 minus z. This is like, in that language over there, this is like b squared. So this is b and this is z. And then as long as we put in, for example, well, if k is an integer, these are definitely going to be rational solutions to this problem. So we have a whole set of solutions to this problem here. Okay, so this is one way to think about it. Now, okay, so how does this get, this seems like a purely algebraic question. How does it come, why do we see the beginnings of number theory here, or continuation of number theory, or any number theory at all? We're just doing some algebra here. Well, a couple of things. Number one, we just want integer solutions, or we just want rational solutions. So that sort of asks the question, when are these numbers going to be integers or rationals, which is sort of a number theoretic question, as well as divisibility of numbers and this sort of thing. Okay, the final thing that I want to mention is that this was the problem that Fermat was studying. This was the exact problem that he was studying for something like c to the power of k equals a to the power of k plus b to the power of k. Or maybe let me change these to n. This was the problem that he was studying this problem in Diophantus's book, and then he decided, okay, what about if instead of to separate a given square into sum of two squares, it is to separate a given nth power into the sum of two nth powers. Okay, it was this point in this book where he says, okay, I know you can't do this. I have a proof. I have a very good proof for this, but there's not enough space in the book to write it. So this is many of you are probably aware of this famous story of Fermat's. This is the problem that he was working on, which is one of the reasons that I picked this problem to demonstrate. Okay, so again, like I said, this is a lightning speed sort of example of one of the things Diophantus did. He also had systems of equations and things like that as well. You've probably seen that in some other classes that you've taken, and we might get to it a little bit more when we talk more about modern algebra and that sort of thing.